Hi, I'm Jeffrey Wang, and I'm Chief Architect at Amplitude. Today, I want to talk a little bit about our distributed query engine, specifically why it's good at what it does, and how that enables us to offer everything we do in Amplitude. So to kick off, let's define the space in which we're operating. It'll be this big circle here, and we're going to call this space real-time, interactive, self-service, product analytics. So that's a lot of words, but each of them is really important, and if you relax any of these constraints, the problem becomes a lot easier, but this is what makes the data valuable. For us, real time means that the data shows in within seconds of when it arrives and is available for analysis. Interactive means that after a user sees a query result, they can ask that next follow-up question they have, which means this query system needs to be both fast and flexible. And then lastly, self-service means that our end user, who is non-technical, for example, a product manager, can answer the questions that they have in mind. All right, so when we're talking about this space, it might be helpful to start by looking at what kind of existing approaches exist out there today. And that'll put our system in context. So at the bottom here, I'll draw a spectrum. And on one end of this spectrum, we'll call this pre-aggregation. And I'll go into a little bit more about what that means in a second. And the other end, we'll just call it SQL. So on the pre-aggregation side, the approach is pretty straightforward. As the data comes in, either interactively or in batch, you compute beforehand what metrics that you're interested in. And once you compute those, you can store them in any sort of system like Redis or Cassandra or even a SQL database. But the point is you're storing the pre-aggregated results instead of computing on the fly. It has a lot of obvious benefits, the most important are which it's extremely fast and it's extremely cheap. Because you decide beforehand what to compute, you can dedicate all the resources to that, and then at query time, it's very easy to put those results together. But it has the obvious big downside of being inflexible. So Amplitude actually started as a pre-aggregation-based system because we knew that fast and cheap was really important to achieve the above. And we actually designed it in a way where we could get decent interactivity. But as we grew, our customers demanded more and more flexibility in their feature sets, and we realized that sticking with pre-aggregation wasn't going to cut it for the long term. So I'll get to how we solve that problem in a second, but let's talk about the other end of the spectrum, which is SQL-based. And I use SQL here just because it's kind of the standard for flexibility, not because all systems are SQL-based. But the point is SQL is an extremely flexible query language, which allows you to express almost any query you're interested in. And so obviously that's the big plus over here. But the downside is, in these big SQL data warehouses that teams run, where they put all of their data in and run arbitrary generic SQL queries, you end up in this really rough trade-off between cost and speed. And in practice, the trade-off is often bad from both perspectives. You both end up with an extremely expensive query system, but you also end up with something that's pretty slow for a lot of the stuff you want to run. And the reason for that is that when we talk about product analytics, a lot of the queries end up being distributed joins. And joins are very expensive in SQL databases, especially distributed ones, which you need for data at this scale. And so that's why you end up with that bad trade-off. So when we were thinking about building Amplitude and how to power our queries, we realized that it wasn't enough to be on this spectrum. And we're not just like a little bit off of the spectrum. We're talking 10x off. And that's a big innovation. Luckily, we don't need to bend any laws of physics here, and instead, we observed a really key common thread among our queries about user behavior. So although it's the case that they get kind of arbitrarily complex semantically, so the specific way that you want to define funnels or retention or what have you, the common thread is that all queries about user behavior and product analytics talk about joining along that dimension of user behavior. And so if you can do that, if you can do user joins in a distributed manner efficiently, you've kind of solved the problem. And so what ends up happening is that we break away from this spectrum, and we end up with our system. So what does it do? It's flexible along user join, so not arbitrarily flexible like SQL, but much more flexible than pre-aggregation. We can do these fast, and we'll talk about how we do that in a second. And we can do them at a reasonable cost. So nothing's going to be as good as computing all of your results up front and serving them. But by limiting ourselves to just the user join dimension, we get kind of the best of both worlds in this trade-off. And that leads to a system that solves our problem. OK, so that's kind of the key insight into how this system all comes together. I want to talk about two of the fundamental architectural pieces that let us actually build this. So the first one is the way we distribute data in the system. So let's imagine that all of these boxes are machines in our distributed query system. So by distributing data, I mean, how do you partition your data among these machines so that you can efficiently use your join? Well, it's actually pretty straightforward. When the data comes in, we'll call this data here, we look at every piece of data is associated with a user, and we just use that user to decide where the data goes. So maybe users 1 and 2 go here, users 3 and 4 go here, and users 5 and user 6 go here. Any number of users that come in, you can kind of decide where it goes. The hard part of this is that we need to partition in this way both for append-only data sets, like event data that comes in, as well as mutable data sets, like properties. And on top of that, this partitioning needs to be maintained even as a customer or data set grows. And we need to repartition and scale up and down as fit. But once you do that, you end up in a situation where on any particular machine, you can look at, let's say this is user 1, you can look at all of their events and all of their properties. And you have all of that information available, which leads right into the second architectural piece of our system that enables what we do, which is the computational model. So instead of something like SQL where you have a specific language in which to express all of your queries, our computational model is code-based, something more akin to Spark. And the point is that in code, you have access to this full user profile, all of their events and properties, and you can compute any data structure using any sort of mechanism you want. And that allows for things like iterative processing, which is often very difficult in SQL. So as an example, one thing that our system enables, which is pretty powerful, is a distributed k-means clustering query. In this type of query, it's iterative in nature, right? You take multiple passes over the data, and it requires some coordination. So to illustrate kind of how that happens, you're running on this machine over here, and your individual worker is computing the centroid on all of the data, all of the users within this data partition. And then the output is some centroid information. We'll just represent as a small dot here. Each of these individually compute their own centroids. But the point is these are small pieces of data. And then you can share this information with each other to determine what to do for the next pass. And then when you iterate on this, you end up with the k-means clustering algorithm. The point here is that even though k-means clustering is a semantically very complex query, something that's actually quite hard to express in SQL, it's also a fundamentally user join problem when your vectors are user behavior. And so the fact that you can compute on the users independently, you don't need any joins within or across the nodes until you get to this centroid step. That means you can do those really fast and in parallel, and then coordinate a little amount of information, and then result in the query that you want. So everything that goes into this system is designed to enable these really flexible user join type queries that enable, again, real-time interactive self-service product analytics. All right, and the final point is our system today processes over 10 trillion events in total. And every day we end up scanning upwards of a quadrillion rows. And that's enabled by the fact that we don't have to do really complex data shuffling, expensive join mechanics, because we have this concept of user joins built in. And that's how we enable product analytics. Thanks.